So welcome back. In this lecture, we're going to discuss Bayesian networks as classifiers. And classification is probably the most common task in machine learning. And it would be interesting to understand how we can use Bayesian network as classifiers too. But we need to understand if it's going to be effective and efficient classifiers and how we can compare them to other classifiers. You're going to see that a very simple classification system that we have in machine learning knows that naive Bayes classifier is actually a Bayesian network. And we know that the naive Bayes make very strong assumptions about the dependence of attributes. And I'm going to see how we can extend those models in order to make those assumptions a little bit weaker. So yeah, let's get started. So now you understand a little bit more about Bayesian networks, and probably you haven't noticed the difference between making a model with a Bayesian network or a probabilistic graphical model compared with the models that we create in machine learning. So I guess first thing that is very clear is that the models we create with Bayesian networks, they are understandable. So it's part of what we call the explainable AI. And it's very important part of the modeling process to understand the domain. I know that we can learn the graph from data, and there are techniques for doing that, but frequently we want to understand the problem, model the problem in a reasonable way in order that the model will be a good approximation for the real problem. You probably have noticed that when we create a model for machine learning, the model is very task specific. So we create a model for classification or regression, and the model will only do that. We only classify the class variable, or we only predicted the target variable for regression. But in the case of Bayesian networks, we can have different queries, and we can have different variables as query variable, and we can have different variables or evidence. And we can use all that information in different situations. For instance, we want to make a diagnosis for a disease. We have a certain exams that were done by the patient, and we can ask what's the probability of a disease given the exams that we have right now. And if this probability is very small, we can ask the Bayesian network how would be that the probability if we increase and have as evidence more exams. So we can make different what-if scenarios and different analysis doing that. But in this lecture, we're going to discuss Bayesian networks as classifiers. So we're going to split all variables that we have for a certain domain, for a certain data set, into two groups. There are attributes and the class variable. And we will try to predict the class variable based on the information that we have for the attributes. I think that's going to be an interesting exercise because we will be able to discuss some topics that we have covered before, like independence, and also some other topics that we're going to see in the future, like learning and inference. And it will be also an opportunity for discussing naive Bayes and a few extensions, and we see that these are very simple Bayesian networks. So in order to make this discussion more concrete, let's take one example. And in this figure here, we have a Bayesian network for the diagnosis of breast cancer. So this diagnosis is going to be based on one exam that's called a mammography. And a mammography is an imaging exam. So basically, we will observe the breast cancer, and it will appear to us as a mass, right, in the image that has a certain size, a certain shape, has a margin that is the border between the nodule and the remaining of the breast, and we can put together with other information and also, for instance, the location of the person, the age of the patient, and so on. So we'll have basically two sets of variables. We have the class variable that is going to be a single variable, that's going to be just a variable for breast cancer that we'll call B. And we have the other variables that will be all attributes. And those other variables, the attributes, we're going to use them as evidence for the Bayesian network. So we're going to observe them and use this information as evidence in order to compute the probability of B. So there are a few things that we need to discuss. One is the type of query. It's clear that we will be interested in the probability of B, and we see how many values B can assume. What are the independence assumptions, right? So there's going to be an important aspects of this discussion, because if we have some variables that are independent from the others, so we don't need to measure those variables. So which variables will be relevant in order to figure out what's going to be the probability of B. And also learn structure and parameters. And in this specific case here, I'm showing you a Bayesian network that was created based on an interview with experts. But in the case that we want to create that Bayesian network from data, what are the possibilities that we can have for classification in particular? And we see a few possibilities in this lecture and a few more in the future lectures. So for this problem, what we want to solve in order to make the classification is to compute the probability of this variable B, as I was saying. And this variable B, in this example, has three possible values. That's null, in situ, and invasive, right? So basically what we are trying to do is to have the probability of B computed, and it's going to be a small table. And in this table, we have only B, and we have three possible values, that is null, in situ, and invasive. And we're going to give one instantiation for the attributes that are going to correspond to the observations for a patient. We're going to instantiate this Bayesian network and compute this probability. At the end, we expect to have one result that's something like, okay, this is 0.7, this is 0.2, and this is 0.1, something like this. And we're going to take the instantiation of B with maximum probability, that in this case it is null, right? And we conclude that the classifier is predicting the class null for this specific patient. So if we have an observation for all the possible variables, but of course B, we call this query the MPE, that stands for the most probable explanation. So as the name suggests, what we are interested in is to find the explanation, that is the value of B that has the highest probability. It's interesting to note that if we have a missing data into the test cases, so imagine that we have to classify one case that has missing data, that would be dealt by the Bayesian network in a very natural way. So what we would do, we would instantiation observe some of the attributes. The other attributes that we cannot observe, that we did not observe, we don't have it in the test case, we don't set it as evidence, and we run a query that is very similar to MPE, that's called the map query. So the map stands for the maximum a posteriori, and it's very similar to MPE, but it allows us to have some nodes that are not observed, right? And we will have to make a little bit more computation, because we have to eliminate those nodes by doing a summation process, and we will see how we do that in when we discuss inference. And also there will be a lecture that will be specific to discuss algorithms for MPE and map inference. For now, we're gonna concentrate into the case that we have a complete data. So we have observations for all attributes for a case that we want to classify. And let's see how we can do that. So the analysis of the complete data case, it's interesting in order to discuss the independencies that occur in a Bayesian network. So when you have the complete data, we have instantiations for all possible variables. So it means that we have a variable breast cancer here, and we have other variables that connect to breast cancer. I'm going to make a chain to make the explanation very simple, but it could be different. And if we have those variables observed, right, we know by this separation that some of these variables will be independent of B. And because we have observed this guy here and this guy here, it will make this variable independent of B. When we say independent, we say that observing this variable will not change the probability of B. And observing this variable here also do not change the probability of B, because this node and this node, they are blocking the influence of those variables to B. So this is interesting, right? So it's basically saying that even though we have this very complex, not very, very complex, but a little bit complex Bayesian network, and we are observing all the variables, not all those variables will contribute to the decision what is the classification for the breast cancer. So it will be important to understand which variables will contribute and which will not contribute. And in order to know that, we can use the concept of the Markov blanket. So the Markov blanket of a certain variable x is composed of the parents, the children, and the spouses of this variable. So it's a very interesting concept. So we have the variable x here. We expect to have parents. I will draw 2, but we can have more or less. We will have children. I will draw another 2 here, but we can have more. And we have the spouses. So the spouses are the parents of the children of x, right? And this is the Markov blanket. We say that if we observe the variables in the Markov blanket, we isolate x from all the remaining variables that we have in the graph. So let's try to understand why that happens, right? So here, by this separation, if we have more nodes here on the top, it will not influence x because it's going to be a causal chain and the parents are going to block this influence. The children, we may have more descendants of x, but because here we have a causal chain that's going down here and we have observed the children of x, it will block the influence. And also very important is to observe the spouses of x, because as we have observed the children and we have this convergent node here, the spouses can influence x, right? So understand that this is the exception that for the d-separation algorithm, and this is going to be not blocked if we have the convergent node observed. So yeah, it should be an interesting exercise here to look at this more complex graph and try to identify what's going to be the Markov blanket. So we have the X node here in the middle. It's going to be our breast cancer. And we have the parents. So the parents are going to be age and location. Good. We have the children. Let me change color. And this is one child, second child, third child. This is also a child, and this is also a child. Okay, I guess we got all of them. And we have the spouses. So this is going to be one spouse. Who else is spouse here? And yeah, I guess it's all. So we see that given those variables, some other variables will not influence the variable x. So we're going to see that the information about size is not going to be used, shape, margin, and speculation. And some variables will not be considered. So we can understand this as a sort of feature selection. So we're saying that these are the main source of information, so these we should consider, but we can be a little bit concerned too because we are not using all the information that we have available, so we can look from these two different points of view. But we need to understand this a little bit deeper in order to get into a conclusion. So let's take a look on the next slide. Okay, so basically this is the same information that we had before, a little bit better organized. Let's take a look at that simpler example. I think that it will help us to understand this idea a little bit better. So we can use this very simple toy Bayesian network in order to get a better understanding. And in this network, we have the variables winter, sprinkler, rain, wet grass, and slippery road. And we can think that the winter will interfere with the rainy season, and also is more likely that you're going to use the sprinkler in the summer when it's hotter than the winter. And both variables, sprinkler and rain, is going to influence if you have a wet grass, and the rain is also make the roads more slippery. And let's think that we're going to have a square variable sprinkler, right? So the variable is going to be b. In this case, we need to see what's going to be the Markov blanket, and in this case, this guy here is a parent, this one here is child, this is spouse, and this slippery road is nothing, so it's going to be outside the Markov blanket. So we expect that these three variables will influence our classification of a sprinkler that can be true or false. So let's suppose now that we're going to make the classification, and that's going to be a very simple case of an MPE inference. So let's suppose that this is our evidence. Remember that we are using the complete case, so we have a instantiation for each variable but b. So in this case, A is going to be true, C is going to be false, D true, and E false. And when you compute the probability of B and see what is the most likely value, it's going to be true or false. In order to do that, I think that the simplest thing that we can do is to use the chain rule for the Bayesian networks in order to compute the probability of B and together with the evidence. So we have this probability of B and the evidence, and according to the chain rule for the Bayesian networks, is going to be, let's look at the network there. It's going to be P of A because A has no parent. It's going to be P of B, given A because A is going to be the only parent of B. It's going to be probability of D given B and C. So D is this node here. It has the two parents, B and C. So correct. Probability of C given A. So C has one parent, that's A, and probability of C given E. Actually, this is wrong. It's going to be the probability of E given C because C is the parent of E. So, okay, and as we know the instantiation E, we can put that here. So we know that A is true, so A is true here. B, we're going to leave that as a variable, and we check for two possible instantiations. And A is true, D is true as well, so D is true. B variable, not C, so C is going to be false, that's correct. Not C and A, and here is going to be the probability of not E, so E is actually, yeah, correct, false, given not C. All right, so we have everything and we need to compute that. So let's take a look at the next slide. Okay, in here we have all the information that we need in order to compute the probability of B. In this case here, we're going to start with B equal true, and we're going to take the probability of A true. Okay, that is exactly here. It's going to be 0.6. It's going to be times the probability of B given A. So the probability of B given A is here. It's going to be 0.2 times the probability of D given B and C. The probability of D given B and C is here, 0.9 times the probability of not C given A. The probability of not C given A is here, 0.2 times the probability of not E given not C. That's here, that's B1. So we compute that, and the result is 0.0216. Okay, we can continue to do that, and now we need to compute the probability of not B given E, and we do that in the next slide. Okay, and now we do the computation for not B, and we're going to be very similar. We take the chain rule for the Bayesian network, and we compute. I have to fix this. This is EC, this is EC, and this is conditional, but we're going to be very similar, right? So we're going to take P of A, now P of not B given A, because we have the not B instantiation, P of D given not B and not C, P of not C given A, and P of not E given not C. And if we multiply and it's marked here, what are the corrective values, we see that the number is smaller than the first one. So our classification is going to be B equal true, because this is the value of maximum probability. And you may ask why we are computing P of B and E. Shouldn't we be computing probability of B given E? Is actually what we are interested, right? So we have the evidence and we want to know what's the probability of B conditional to that evidence. And for classification purposes is actually the same thing, right? So we can see that if we say that probability of B given E is the probability of B and E divided by the probability of E. And we can compute the probability of E by using case analysis. So it's going to be the sum of BE and not B and E. So it's actually these two values here. So what we are doing here is just a normalization. So we sum the two values, and let's call it Z, and we divided this by Z and the second one by Z2. So it's going to just be a normalization. We will not change the rank of the two numbers. All right, so but another piece of information here that's very important is what in fact is making a change or make a difference in order to have these final numbers and decide that B should be equal true. It's the most likely. The value is the value with the highest probability. Look at that here. We have the same term P of A. So we can, cancel this because as we are comparing the two values, it's not going to change anything for us. These two terms here we cannot cancel because one depends on B and the other one is not B. The same thing for here. Here it doesn't matter. It's going to be a constant that being multiplied in both equations, and here also constant. So actually what's making difference is just these two terms here, right? They are the terms where B appear. So these are the conditional probabilities where I have the variable B. So in this case, we are just using the information that we have here and the information that we have here, because these are the tables where B is present. So you may be asking something like, well, it's true that because we saw that the Markov blanket are the relevant variables in order to decide to isolate B from the remaining ones. So what you're showing here is actually saying that the theory is not correct because we are just looking at the nodes B and D. And we say, no, the theory is correct, because if you look here, we see that those conditional probabilities will take into consideration the values of the variables that are into the Markov blanket. So they are important. They will tell us exactly what is the role that we should take from the conditional probability. So we see that the Markov blanket involves A, and A is here. We know that the Markov blanket involves C, C is here, and also D, and D is here, and together with the variable B. But at the end, the probabilities that we are considering are just the ones that involve the variable B, that is the class variable. So in the end, we have this, right? So we come back to our more complex breast cancer example, and we look at which variables, which nodes involve a conditional probability table that has the variable B, that is our class variable. We see that is very small number of nodes that have this. There are these nodes here that are marked in green. Okay, so how we can interpret that, right? So it has the feeling that we are not using all the information that we have in the Bayesian network. We are just using a few probabilities in order to make the final decision. Note that this is only valid for the complete case. If you have missing values, so what's going to happen is that some of the missing values may be the variables in the Markov blanket of the node. So in this case, the other variables may influence that variable. So it's very important to understand that we are just discussing the complete case. But even the complete case is very common. So we frequently have complete case when you are classifying instances in a data set. So it's an important thing to consider. So in some way, Bayesian networks are not using all the probability that we have available, just one subset of them. Some authors say that we are doing a sort of a feature selection and only considering what is most relevant. Other people may say, okay, that's not optimal for classification in the complete case because we are losing too much information. And we're going to see in the next slides are different ways of doing classification. One of them is actually the opposite of this. We're going to take what we call the naive Bayes and going to consider all the nodes together to be influencing the class directly. And in this case, it's going to be, the complete extreme, because all variables will be relevant in order to decide the classification. So let's continue the discussion in the next video.